Assalamualaikum. In the last lecture we talked about ideal transformer. In today's lecture we shall discuss real single phase transformers. We shall learn the differences between a real transformer and an ideal transformer. From our discussion in the last lecture, we know that an ideal transformer is a lossless device. That is, in the last lecture we proved that whatever is the input power to an ideal transformer, the same is the output power. That is, it is lossless. Secondly, the core of an ideal transformer is also ideal. That is, reluctance of the core of an ideal transformer is 0. So this statement has two implications. Firstly, since the reluctance of the core is 0 and reluctance of free space is much higher, therefore all of the flux will be constrained to the core and there will be no leakage flux. In an ideal transformer, there is no leakage flux. Furthermore, no magnetization current is required for an ideal transformer. We shall talk about these points in more details. Compared to this situation, in case of a real transformer is not a lossless device. There are different losses. Firstly, there are eddy current losses. We have talked about eddy current losses in previous lectures. The changing flux not only links with the coils of the transformer but also links with the core of the transformer, which produces this changing flux produces an EMF which causes the current to flow in the core of the transformer, and that flow of current results into losses which is called eddy current losses. In addition to that, there are hysteresis losses, and hysteresis losses, these are proportional to the area of the hysteresis loop, the orientation and deorientation of the domains in the core of ferromagnetic material. That is the reason for these hysteresis losses. These two losses together, these are called core losses. In addition to that, the current flowing in the primary and secondary winding, that also results into I square R losses. The windings of the transformer, these are made up of copper. Copper, although it has negligible resistance, but still it does have some resistance. Therefore, there are losses in the windings of the transformer. These losses are called copper losses. So, a real transformer is not a lossless device. There are different losses in a transformer. Furthermore, reluctance of the core of the transformer, that is not 0 for a real transformer. Therefore, the flux has multiple paths for flow. It can flow through the core of the transformer. It can also flow through the free air, since reluctance of core is not equal to 0. So there is also leakage flux in a real transformer. And furthermore, some current is required to cause the flux to flow in the core of the transformer. That current is called magnetization current. So in an ideal transformer, there is no magnetization current. In a real transformer, there is also magnetization current. So we shall talk about all these points one by one in more detail. We start with the first point, that is the leakage flux. So in an ideal transformer, this reluctance of the core is 0 and all of the flux is constrained in the core of this transformer and there is no leakage flux. Compared to that, in a real transformer, flux has one path through the core. So most of the flux will be flowing through the core of the transformer. However, there will be some of the flux lines will leak into the air. This flux is called leakage flux. So this leakage flux, if the current is also flowing in the secondary winding, so there will also be leakage flux on the secondary side. What is implication of this effect? So to study the implication, let's discuss it mathematically. In the case of a real transformer, the total flux, different turns of the coils have different flux linkage. So we define the average flux linkage. So average flux linkage with the primary winding, flux linkage with the primary winding, that consists of two parts. That is the flux which links with the primary winding as well as the secondary winding. Let's call it phi m, the mutual flux, and the flux which leaks into the air on the primary side, so leakage flux on the primary side. Similarly, the average flux linkage with the secondary winding, that is given by two parts, the mutual flux and the leakage flux on the secondary side. We remember that flux and induced voltages, these are related by the Faraday's law, which is given by this expression: E induced is equal to N d phi by dt, with negative sign by the Lenz's law. So if we use this relation, the voltage on the primary side, this voltage Vp of t, that is given by Vp of t, that is equal to the number of turns on the primary side multiplied by the rate of change of flux linking with the primary coil, and that is equal to minus N d phi m by dt, Np minus Np d phi Lp by dt. Similarly, the voltage on the secondary side, this voltage Vs, that is also related by this relation Vs of t, that is equal to number of turns on the secondary side multiplied by rate of change of flux linking with the secondary coil, and that is equal to Ns d phi m by dt minus Ns d phi Ls by dt. And the ratio of the primary and secondary voltages Vp of t over Vs by t is given by minus Np d phi m by dt. For a good design of transformer, this leakage flux is much smaller compared to the flux which flows through the core. So for a good transformer, this term, likewise this term, can be neglected, and therefore this expression is approximately equal to Np by Ns. Hence, for a real transformer, this relation which we have already studied, that was for an ideal transformer, this relation, that is the ratio of primary and secondary voltage is equal to the turns ratio, that was exactly valid. However, for a real transformer, this is only approximately applicable. With this discussion, we have also derived the relation, that is Vp over Vs, that is equal to Np over Ns. We had previously just written it without any proof for this statement. So for a real ideal transformer, since there is no leakage flux, this expression is exactly true. For a real transformer, this is only approximately true. Before we talk about the other differences between a real transformer and ideal transformer, let's also talk another associated expression. That is, we have already also talked about the ratio of primary and secondary winding, that we learned that is given by this expression. However, we have still not proved it. So let's prove it before talking about other differences between real and actual transformers. This expression is exactly applicable for an ideal transformer and is approximately applicable for a real transformer. We know that MMF is equal to flux multiplied by reluctance. We have already studied this expression. For this transformer, ideal transformer, there are two sources of MMF. One source is this one, which causes the flux to flow in this clockwise direction. There is another source of MMF. If current flows in the secondary winding, then this current in the secondary winding will produce an MMF which will cause the flux to flow in opposite direction. So there are two sources of MMF. This MMF is equal to, we already remember, number of turns multiplied by the current in the primary winding. That is one source of MMF. Another source of MMF is number of turns on the secondary side multiplied by the current on the secondary side. Since the two sources of MMF, these are opposing each other, so total MMF is equal to difference of these two MMFs, and that is equal to flux multiplied by reluctance. So what is reluctance of an ideal transformer? Reluctance of an ideal transformer is 0, which means that NP multiplied by IP minus NS IS, that is equal to 0, which gives you this relation IP of T over IS of T, that is equal to NS divided by NP. Number of turns on the secondary coil divided by number of turns on the primary coil. The phasor representation of the same expression is written over here. Again, this expression is exactly true for ideal transformer. It is only approximately true for a real transformer. So we were talking about differences between ideal transformer and a real transformer. In an ideal transformer, if there is no secondary current, there will be no primary current. However, what is observed for real transformer is that even if the secondary is open circuited, some small current flows on the primary side. This current consists of three ingredients. Firstly, the magnetization current, which we are going to talk just now. And secondly, the current to incorporate the eddy current losses. That is, some current will be required to incorporate the eddy current losses, because if there are some energy being consumed in the core, that has to be supplied by the source, and that is through this current. And also the hysteresis loss. If there is loss, there is some power consumed in the core of the transformer that has to come from somewhere, so that comes from the source connected to the primary winding. So the current, if there is the secondary is open circuited, in the primary some current will be flowing. That current is composed of three parts: the magnetization current, eddy current to incorporate the eddy current losses. Eddy current is flowing in the core, and the power which is being consumed in the core, that has to come from somewhere. That comes from this voltage source and through this current. Likewise, hysteresis loss is in the core, and the power which is consumed in the core, that comes from the voltage source connected over here, and that is the source of current. So first we talk about the magnetization current. So we already know that MMF is equal to number of turns multiplied by the current. For an ideal transformer, the core is also ideal, that is, reluctance is equal to 0. Hence MMF, which is equal to Ni, which is equal to flux multiplied by reluctance. So MMF whatever is the flux, since reluctance is 0, so MMF is equal to 0. That is, the current required is equal to 0 for an ideal transformer. However, for a real transformer, the situation is different. We have already talked about the magnetization curve. Here we have MMF and here we have flux. For a real transformer, MMF and flux, these are related by this curve which we called magnetization curve. What do you think is the magnetization curve for an ideal transformer? Can you sketch the magnetization curve for an ideal transformer? So whatever is the flux, that is for this flux, MMF should be equal to 0. That is not the case over here. In case of a real transformer, for this MMF, for this flux, we have this much MMF. Here, whatever is the flux, this one, whatever is the magnitude of flux, so MMF is 0. So the magnetization curve for an ideal core is given by this graph. The same, similar to an ideal conductor. What is relation between voltage and current for an ideal conductor? That is this one. So the same is the situation for an ideal core. And this is magnetization curve which relates MMF with the flux. What do you think is the curve between the magnetization current? MMF is basically nothing but number of turns multiplied by current, the magnetization current. So what do you think is the shape of the curve between magnetization current and flux for a real transformer? So it should be of the same shape because n is constant. So whatever is the shape between MMF and flux, the same should be the shape of the curve for the magnetization current and the flux. So this is the graph relating the magnetization current and flux. Hence, if we are given with a graph of flux, we can find corresponding amount of the magnetization current. For that purpose, let's take this situation. So suppose we have applied the primary voltage to a transformer Vp given by Vm cosine of omega t. We have applied this thing, and we know that flux that is given by our Vp of t, that is equal to d phi by dt. That we know, n d phi by dt. Therefore, flux that is equal to the integral of the voltage 1 over np Vp of t. If we integrate both the sides, and np is the number of turns on the primary side, we have this expression. If different amount of flux is linking with different turns of the coil, we can also incorporate that effect by taking the average flux. Therefore, this phi bar, by integrating this thing, Vp is Vm cosine of omega t, we have. So if we apply this sinusoidal voltage with peak value of Vm to the primary of the transformer, this much flux will be flowing in the transformer. Corresponding to this flux, we can plot the magnetization current. So this flux plotted in the time domain. This is time axis, and we already know the plot of this curve will be sinusoid. So this is graph of flux versus time. If we are given with an amount of flux, we can have a graph of magnetization current, corresponding value of the magnetization current from this graph. For example, if this much is the flux, then this much will be the magnetization current. So for this flux, we can have a sketch of magnetization current. This is now time axis. You can have a plot of it in different ways. So this is somehow more convenient. Here, this is the time axis, and this axis is the magnetization current. For example, corresponding to this much amount of flux, that is zero flux. What is MMF? What is magnetization current? Flux, vertical axis, flux 0. So magnetization current is also equal to 0. What is the magnetization current for this much flux? This much flux. This much flux means this much flux. For this much flux, the magnetization current can be read from the graph. So that is this one. Similarly, corresponding to this much flux, this much, what is magnetization current? This is magnetization current. So what we can do is, corresponding to each point on this graph, we can locate the required amount of the magnetization current. By joining all these points, we have this curve for the magnetization current. Why this kind of peak over here? Because in the linear region, small change in flux will result into small change in the magnetization current. However, once the graph enters into the saturation region, small amount of change in the flux will result into large change in the magnetization current. So for this much flux, this much magnetization current will be required from here, right from this graph. So for a given shape of the flux, we can determine the magnetization current, required magnetization current. Although flux is sinusoidal, however, the required magnetization current is not sinusoidal. If we plot this flux and the magnetization current on the same graph, we have this thing, time axis, and the flux this is flux, and what is the applied voltage? Vp. Vp is cosine omega t, and this is Vp of t. What is graph for Im? Graph for Im is sketched over here. That this current is in phase with the flux. However, it is not sinusoidal. The fundamental component of this magnetization current is in phase with the flux. There is a peak due to saturation over here. So the graph for the magnetization current, that looks like this one. So this magnetization current is in phase with the flux and lags the applied voltage by an angle of 90 degrees. This information that will be useful when we will be obtaining the equivalent electrical circuit for a real transformer, that is the magnetization current, which is depicted over here, Im of t, that is 90 degrees, that lags 90 degrees from the applied voltage. So we have talked about magnetization current. The second component of the primary current, which is flowing in the primary winding even if there is no secondary current, is required to supply the eddy current losses. So we know that eddy currents are, since the changing flux links with the core of the transformer, therefore voltage is also induced in the core of the transformer. The induced voltage in the core of the transformer is also proportional to the rate of change of flux, and hence eddy currents, the eddy currents, these are also proportional to rate of change of flux. So if we sketch the graph for eddy currents, that is graph of the current required to supply the eddy current losses, that should be of this shape. Here is the graph of flux, and we know that this flux primary voltage was given by this graph. This is graph for primary voltage, and this eddy current, the current flowing in the primary winding to supply the eddy current losses, I call it eddy, that is also proportional to d phi by dt, and therefore this current is in phase with the primary winding, because Vp is also proportional to d phi by dt. So eddy current, that is also in phase with the primary voltage. This current is IE, the eddy current. It is basically not the eddy current, it is the current flowing in the primary winding, and that current supplies the power losses due to eddy current losses in the core of the transformer. And this current is in phase with the applied voltage Vp of t. The third current, third component of the primary current, which is flowing in the primary winding even if the secondary is open circuited, that is required to, that current is required to supply the hysteresis losses. You know, the hysteresis is a nonlinear effect, and it only adds some nonlinearities. Therefore, these two currents together, we call them the these two losses, we call them the core losses, and the current required to supply both of them, that is the eddy current and hysteresis, that current will be of some shape like this one. That is, it will only add some nonlinear effect to this current IE. I have written IE over here, so I must also write IE over here. So this current hysteresis only produces some nonlinear effect over here. So that current is, so this current, this blue line is IE plus H, eddy current to supply the eddy current losses and to supply the hysteresis losses, that is shown over here. We have already sketched the curve for magnetization current. Magnetization current was in phase with the flux, however it was very high when the flux was peak, and otherwise it was in phase. The fundamental component of this magnetization current is in phase with the flux. So this current is the magnetization current, as we have already talked about. So in the primary of the transformer, there are three components of the current which are flowing. even if secondary is open circuited and no current is flowing in the secondary. First component is the magnetization current. The second component is required to supply the eddy current losses. Third component is of the current, primary current, that is required to supply the hysteresis losses. These three components together, these are called excitation current, i.e. excitation current, that is equal to the sum of magnetization current plus this current. That current which flows in the primary of the transformer, even if the secondary is open circuited, that current is called excitation current. We can see that this magnetization current is the fundamental component of this magnetization current is in phase with the flux, that is, it lags the applied voltage by an angle of 90 degree, and this current IE or IE plus H, the fundamental component of this current, is in phase with the applied voltage. This information will be very useful. The understanding of this information is required when we shall talk about the equivalent electrical circuit of a transformer in the next lecture. Another important thing to observe is that this IE and similarly IE plus H, that is the fundamental component of this one, is in phase with the applied voltage, and you already know that power, that is equal to VI and cosine of the angle between the two. So angle cosine of 0 is 0, so this component of current results into losses, that is IE plus H, that causes losses. However, this magnetization current, the fundamental component of the magnetization current, lags the applied voltage by 90 degrees. That means cosine of that 90 degree is 0. So this current, the magnetization current, does not result into any energy and power losses. So in the next lecture we shall talk about the equivalent electrical circuit of a real transformer.